So just a little information for you. Ooh, man. More for the people here at this first table. This morning I let my dogs out of the house to do their routine, and I hear them yelping, and one of them barking, the other one yelping, and anyway, they got sprayed by a skunk. So if you've ever had that happen to a dog, it's not fun. And so I was...
Tomato juice.
Well, I tried something else. I tried hydrogen peroxide with baking soda with soap, and...
Dawn.
Yeah.
Dawn with tomato juice.
What's that?
That sounds dangerous.
It's supposed to be like some chemical chemist found a way to neutralize the odor, whatever. It worked okay. It wasn't great, but it's better than it was when they got sprayed initially. So I'm telling you this because I smell like a skunk. My hands smell like skunk. I smell skunk all over me right now. So if you smell that, it's not my cologne.
So I'm trying a new friction.
Yeah, I'm trying this new thing. Okay, so I've had an interesting morning. Started with that, then I came in. They wanted me to substitute again, so I had to substitute this morning, and so yeah. But I'm happy now. I'm here. Everything's good. Right? You ready to go? So you may have had some trouble with your homework because we didn't finish the section completely. So I will entertain any questions that you might have out of homework first.
65.
65. What do you have?
I got the right answer for 65. I just wanted to know how you wanted us to notate it specifically.
Okay, so let me take a look first. We're in 3-1. $65, and then which one?
55. Just the notation.
55.
I got the right answer. I just wasn't sure on how you wanted
Okay.
us to. Because
All
the
right.
book does it different.
Okay, so I'll do each one of those. 55 is pretty straightforward. G of x equals x over x squared minus 16. And we are asked to find the domain. So the domain, we're looking for anything that might cause a problem here when we try and actually plug values of x in. We don't have any square roots or even roots, so we don't have to worry about that. We're really just focusing on division by 0. And it is possible to get division by 0 here, right?
Yes.
So I want to take a look at this. I don't want that to be true, right? I don't want the denominator to be 0.
No.
So what I could do is start working with this. We don't usually like to work with a non-equation like this. We usually like to just leave it as an equals. And then just remember at the end, we don't want those as our answers, right? So just working with this, how did you do this? Did you factor?
I recognize there's a difference between squares.
Okay, so you did a factoring. X plus 4, x minus 4.
Well, what I really did, I just kind of looked at it, and then I just kind of worked backward from there. Like, okay, do I know, will factor to this to give me 0, and then I worked from there.
Okay, either way.
It's the same thing.
Yeah. You can move the 16 over to the other side, take square root on both sides, do plus or minus 4. Or you could factor it and then set each factor to 0 and get same two answers. So these are the two numbers that will actually cause this to be divided by 0. So we don't want those, right? So as far as the number line is concerned, we do not want negative 4. We do not want 4. Anything else is okay, right? Like that. So how do we say this? Well, in interval notation, which is the notation I want you to use in here, everything to the left of negative 4 forever is written negative infinity to negative 4 with parentheses on both. Always putting parentheses on infinity, and then putting on parentheses on negative 4, because remember we talked about this, there's no number closest to negative 4, so that's the way we notate it. And then we want the stuff between negative 4 and 4, so I would write it like this. Parentheses again.
I'm sorry. You don't need the U and
Yeah, and then because these are two different intervals, I'm going to union them together. And then I have a third set of numbers, which is over here. It's everything from 4 on to infinity. And again, I need to union that together.
Okay, I just want to make sure, because it looked kind of funny, it kind of, I guess, it's like, oh, wait a minute.
Yeah. That's okay then?
Yeah,
Okay.
I got the right answer, I wasn't sure on how exactly.
How to write it? This is the way I prefer you do it, and it's really because of where we're headed that you be comfortable with that notation. Any questions? Okay, number 65 was square root of t minus 4 over 3t minus 21. And this is the function capital P of t. So what sort of issues do we have going on here? What do we have to be concerned about?
Possibility of dividing by 0.
We could have division by 0. We could also have a negative in the root. So let's look at these issues separately. First of all, 3t minus 21. I don't want that to be 0, right? So this one's kind of, we can work with this one, leaving it as a not equal to, because it's an easy equation to solve. It's linear, right? T cannot be 7. So because that's kind of a clean, easy thing to work through, I'm just going to write that. T can't be 7. And then the other thing we have to worry about is that we need the thing under the root, which we call the radicand, we need that to be greater than or equal to 0. It's okay to be 0 because the square root of 0 is 0.
It just can't be less than.
Just can't be less than. So this is a linear inequality. All we have to do is move the 4 to the other side. T must be greater than or equal to 4. And then when we combine those two, if we look at this on a number line, this one says, all right, everything from 4 on to the right, including 4. So it's okay to be 4. Everything over here forever. But then when you go back and look at this one, it says, well, hold on, T can't be 7. So we need to eliminate 7 from this solution set. So we will have 2 intervals of numbers, right? Everything between 4 and 7, including 4. So bracket 4 to 7, parenthesis on the 7 because we can't be 7. Unioned with everything from 7 on to infinity. Anybody have a piece of paper that you're willing to sacrifice? Sure. Yeah? Okay. Try not to go off onto tangents like in this class and get off topic because we really don't have time for it. But we've been talking about infinity a couple of times here. And I wanted to show you something. Strip of paper, right? How many sides would you say the strip of paper has?
4.
Okay, if you're counting the edges as sides, right? So you have like top, bottom, then you're counting this edge as a side. So then you, okay, so let's say the sides don't count, okay? So there's no depth to it, it's just a sheet. Then it would have 2 sides, right? 2 sides on this sheet. Okay, so if I take this sheet and I keep this end, just hold it there, take the bottom end and I twist it one time, and then I paste these 2 together and I tape them together, which I don't have tape. I don't see a stapler up there. So if I put those 2 together, I get this. It's all right. I think this will work. Okay? So you can try this on your own at home if you want. You take this now, and the question is now, how many sides does this sheet have? Still 2?
It depends on the way you're looking at it.
So like when it was like this, I could put my fingers on the 2 different sides, right? My fingers are on 2 different sides of this sheet. If I take it, I twist it one time, and I paste it together like this, then if you actually start at your thumb and you go around the sheet, you will come back to your finger, and then if you keep going around and follow around, you'll be back at your thumb.
So 1.
So your thumb and your index finger are on the same side of the sheet. And this is an example of a surface with one side, a one-sided surface. All right? This is studied in a class called topology, not topography, like hills, topology. Sheet, right? you would just keep walking. You would never hit a wall. Whereas if you did this, you're a little ant. You've got these boundaries you can't go past, right? So it's kind of infinite, isn't it? Kind of? A little bit? Anyway.
I see
Okay.
where you're going.
It's just an idea of infinity, like where does that symbol come from? Kind of, not saying that's where it's from, but it's that concept is there. Other people just call this lazy 8. It's like a math joke. Like math dorks like that joke. It makes math dorks chuckle. Lazy 8. Yeah, I don't find it so funny. Okay. New stuff. Today we need to pick up with difference quotient, right? We did one example of difference quotient. That was it? We didn't do difference quotient? Oh, I talked about it geometrically. Okay, yeah, that's right. So we came up with a formula, right? And I tried to justify where the formula came from. But I told you all you need to do is be able to mechanically in this class do difference quotients. So I have 4 examples of difference quotients that I'd like to do. F of x is negative 2x squared minus x plus 3. So we want to evaluate, for each of the following, compute and simplify the difference quotient. So does anyone remember from last class, the formula is up here, right? F of x plus h minus f of x all over h. Does anyone remember what our goal is whenever we actually use this?
Yes.
What is the goal? Good. It's to somehow do this with a particular function we're given, and hopefully we will get that h to cancel, right? And what that allowed us to do was, I tried to show you visually, right? Did I draw a picture? Did I show you the picture of this? Right, we're trying to move one point closer to the other one, right? And so on the graph, we're trying to connect this line right here, this slope. We're trying to move this closer. Now, in my notes, I actually have an interactive image of this. So let me back this thing up. So I have an initial point x, right? I plug that value into the function, I get x f of x. I take some second point, which is x plus h, plug it into the function. Those are the coordinates of the point. Slope of the line connecting them, right, is rise over run. Here's your rise, here's your run. This is what I told you in class last time. We draw this line, and then what we do is we try and move this point over, and what you'll notice is that the slope of that line is getting closer and closer to something here, right? Now if I zoom in, I can go even closer, and it's approaching something. But when I get there, when I get right on top of it, right? When I get on top of it, then I have division by 0, don't I? Because they're the same point. But the workaround for that is to be able to compute this and get the h to cancel. If you do that, then you won't get division by 0. So let's do this. Tell me what this difference quotient would be for this function. So what is the top left corner? What is this going to be? We're taking x plus h and plugging it in here, replacing this x with x plus h, this x with x plus h, right? So let's do that. Negative 2. X plus h, I have to have that squared, don't I? Minus what? X plus h, in parentheses again, right? And then plus 3. You all with me that that's just the top left corner of that difference quotient? So far. Now what I need is the top right corner, right? And I need to subtract it. So this is the part that a lot of people mess up, the subtraction. You will have to subtract everything that f of x is, right? The whole thing. So I recommend putting in parentheses your f of x.
The whole thing, negative 2x squared
Yep, negative 2x squared minus x plus 3. So that is your top right corner. And again, star, 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 like don't forget the minus there, right? All of this over h. And now we get to multiply this stuff out, right? Clean it all up. Hope to get an h to cancel. Negative 2 x squared plus 2xh plus h squared. So I'm mentally squaring x plus h. So I'm doing the FOIL in my head and I'm collecting like terms. You might need to do that on the side, but eventually you get to that, right? So that's this. Then I can distribute minus x minus h plus 3. Over here, because of this minus, I can pass it through the function f. It'll change all the signs. Plus 2x squared plus x minus 3. The entire quantity divided by h. Any questions? What's next? Oh, go ahead.
I was working on that, on the homework,
Uh-huh.
and I guess I messed up on that negative symbol.
The negative, yeah, that'll get you. And once that's done, you'll never recover from it because you'll never get the h to cancel.
Yeah, but I understood.
You understood the...
concept.
Okay, good. So should I pass this negative 2 through next? Yeah? So here's where we'll be. This equals negative 2x squared minus 4xh minus 2h squared minus x minus h plus 3, plus 2x squared plus x minus 3, all of this over h. Now this is the part where when we clean things up, something good should happen. So let's see. Negative 2x squared and 2x squared are gone. Anything else? Plus 3 minus 3. Anything else?
X.
The plus x and negative x. Anything else? That's it, right? We should get an h to cancel. Let's see, because everything that's left, right, has an h. All right, that's it. All over h. So I'm gonna factor an h out of the top. Don't forget when you factor an h out of that last term, right? When you factor an h out of here, it's a negative 1 at the end. Do y'all agree with that factoring? Now cancel the h's. So your answer is negative 4x minus 2h minus 1. That's the difference quotient. So the slope of the tangent line, or the slope of the line connecting those 2 points, should be this. And now if you let h go to 0, it's going to move the 2 points together, isn't it? And we can do that because if I let h go to 0, the only thing that's going to get killed off is this piece. There's no division by 0 anymore. So we had a little workaround there. Now that's a polynomial function, right? That's a quadratic function. But in a calculus class, you have to be comfortable plugging pretty much anything. Doing a difference quotient for any function, not just quadratics. So that's what the rest of this is. Let's see how nasty this gets.
And that is always the formula that we will use.
Yep, that is the universal formula for difference quotient. That was something I was going to ask you. The difference quotient formula never changes. The only thing that changes is the function you're actually finding the difference quotient of. So
Is it that's just, I guess, why, I guess I'm asking.
why is that the function that or why is that the difference
Why is
quotient?
that the only formula? Because like quadratics, there's different ways to go about doing things.
It's because of the picture I showed you. What we're trying to do is we're trying to create this slope. And we're picking a point and a point next to it, x plus h, sliding the point over. When we do that, that difference quotient naturally falls out. of that process, of that procedure. All right, so let's do the difference quotient for this one. So I need, again, to set it up, f of x plus h minus f of x all over h, which should be, all right, what's the top left corner of this?
1 over
X plus h cubed, the whole thing, right? Like that. It is not 1 over x cubed plus h cubed, right? It is not 1 over x cubed plus h. It is not 1 over x cubed plus h, right? Do you see the mistakes someone would be making with those? Right? Oh, I'm just going to take this and I'm just going to say plus h. That's not what this means. It's this x plus h plugged in right there for the x. So these are wrong. Minus, right?
minus 1 over x cubed.
1 over x cubed. Now I don't need parentheses there because I'm not going to get in trouble because there's only one term. So I don't have to worry about distribution of a negative. So that would be safe to do it that way. And then over h. Wow, how are you going to get an h to cancel from that?
I guess the first thing we do is solve the x plus h cubed, right?
How do you mean solve? Or what do you mean?
Maybe lengthen it out a bit.
Work on the numerator.
Work on the numerator? How do you mean work on it?
I guess.
Solve the equation for the, keep the 1 plus
Come
over x
multiply
plus
x
h
squared
minus.
on this side and then x plus h, sorry, cubed.
Okay, so I'm hearing different things.
I'd say just try.
I heard solve, which we want to be careful. When you say solve, you mean you have an equation trying to find a solution. You say simplify. Simplify, that would be good. You could maybe combine these, work with the numerator, try and combine these into one fraction, right?
Yes.
I mean, that's, remember, point A, point B, we're trying to get there. That's a legal move. We can combine. We can get those numerators together, or those fractions in the numerator together. Let's do that, and let's see if this gets us anywhere. So what I would need to do is find an LCD. At the end of the day, what I'm going to do is have to multiply over here, top and bottom by something. Over here, top and bottom by something. So what's that something going to be on this one? X cubed. X cubed over here. X plus h cubed. X plus h cubed. Do you all see that? Common denominator. And so this fraction right here becomes x cubed over x cubed times x plus h cubed minus, this one becomes x plus h cubed over x cubed times x plus h cubed again, but that whole thing is over h. Yeah? Now we can put these two together, right? I've seen people do this before, where they do this step, then they say, I can cancel that out and cancel that out, and then they're right back to where they started, right? Keep in mind what you're doing here, right? We want to put them together, so that we want it to look like this. So at this point, my new numerator is going to be x cubed, take away this numerator, x plus h cubed, over the common denominator, x cubed times x plus h cubed, but then that's all over with the big division bar, h, right? I still don't see any h canceling. Do you? Do you see an h canceling there? Is there anything else we can do then? The what? Can't do these because you have subtraction between the two, so you can't.
Would it be too early to suggest moving the h out and turning it into multiplication?
Like bringing this out here?
Yeah, as a 1 over h.
That's okay, but you still don't have an h that you're going to be able to cancel with. So any suggestions?
Maybe try and get h out from underneath.
Out of here? Let me write this for a second. That's what this is, right?
Yeah.
So what was your name again, sir?
Ryan.
Ryan. Ryan's suggesting we flip this up here like this, or we can do it in the back. And it would make it look like this. Do you all agree that this would be the same?
Yeah.
Without this? So if there's going to be an h that's going to cancel, where's it going to need to come from?
The numerator.
This numerator, okay?
That's what I was-
Keep that in mind. How are you going to get an h out of the numerator?
Factor the x plus h cubed.
Cubed. That's correct. But terminology would be expand, expand it. So factoring would be turning it into this. The other way would be expansion. Okay? So that's a good suggestion. Why don't we go and figure out what's x plus h cubed? Well, that's x plus h times x plus h times x plus h, right?
Binomial theorem.
So you could use the binomial theorem or what's called Pascal's triangle for that. Have you seen that before? Yeah?
I completely
You said
forgot.
Pascal's triangle? How many of you have seen Pascal's triangle or binomial? No? I think it might be worth looking at. So this is equal to, let me just tell you what it's equal to if you did it. X cubed plus 3x squared h plus 3xh squared plus h cubed. That's what that would be equal if you were able to multiply it all out, which you could by hand. It would take you a little bit of time. All right? That's what it turns out to be. But my way was a little faster, right? Because I just knew it. I don't have them all memorized, by the way. I'll show you how I did that in a second, but let me finish the problem. Can I do that? So this to here, we're good? Trusting that we can go from here to here? So what happens here is we get the x cubed on top, right there, minus all of that. And that minus sign has to distribute, doesn't it? So it's going to be minus, do you want me to distribute now, or you want parentheses in that?
No, just
Distribute? So minus x cubed minus 3x squared minus 3x squared h minus 3xh squared minus h cubed. That's the new numerator.
Is that a minus or a plus h cubed?
Where? Here?
Yeah.
This is plus.
All right.
But remember, I'm subtracting. I'm subtracting whatever this turned out to be, right? This turned out to be this. So when I subtract it, every single one of these gets subtracted. With me? That's all divided by, not yet, that common, right? Common, and then all of that's divided by h. Okay? Do you see what happened when we did that? You see the good news?
Yes, you can cancel out the x cubed.
You can cancel out the x cubes. And as little as that seems, as far as what we've gained, everything else has an h in it. Right? What's left in the numerator has an h. So what I can do now is I can say this is equal to, let's take this and factor an h out. H, negative 3x squared minus 3xh minus h squared. All of this over the common denominator. All of that over h. Does anybody have any questions? Can I cancel those h's? Yeah? Because remember it's h over 1, and then you flip it, and the h's would cancel. So I'm just going to cancel them here. And that expression is your answer. Just leave it like this. Negative 3x squared minus 3xh minus h squared over the common denominator, x cubed times x plus h cubed.
So
And-
basically, for the difference quotients, we don't really care about whether or not there's x's or h's remaining in it, so long as
Nope.
we get that bottom h.
That bottom h was the division by 0. That's what was causing, that's what was preventing you from putting those 2 points on top of one another. But once you have a specific function, you can actually go through a process that we did, and you can eliminate that problem, which is nice.
That actually makes sense now.
Oh, the triangle, yes. So I'll show this to you.
You call it Pascal's triangle?
It comes from Pascal's triangle. Let me just write it out first for you. Okay, so if I take x plus h and I raise it to the 0 power, anything raised to the 0 power is 1. I'm putting the 1 way out here for a reason. Everyone agree with that? Okay. If I take x plus h and I raise it to the first power. Anything to the first power is itself. This is x plus h. All right, if I take x plus h and I say for us to square it, then most of you were okay with the idea that this would be x squared plus 2xh plus h squared. Yeah?
So you're just adding those two down?
Yeah, so let's see. There's something happening here. There's a pattern. The next one, I told you, is x cubed plus 3x squared h plus 3xh squared plus h cubed. And I'll give you one more so that maybe you can see the pattern. The next one be x to the fourth plus, what do you think?
3x cubed.
Not quite. 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the fourth. Okay, so now let me point out the pattern. You ready? Just don't worry at all right now about the numbers, just the letters, okay? And let's start with this one because it's easier to work backwards. This is the fourth power, right? Notice that what happens is the x starts to the fourth power and there's nothing else with it, right? Just watch the x's as you move across. X to the fourth, cubed, squared, first power, gone. Now look at the h's. The h's is reversed of that, isn't it? No h's, one h squared, h cubed, h to the fourth, yeah? So what happens whenever you have this, it's called a binomial expansion, is that this right here, the x, it starts as the same power and just goes down. The other one, the other term in here, the h in this case, starts by not appearing and then it starts appearing and keeps going up by a power. Okay? So I still am not going to not worry about the numbers right now. With that in mind, though, here's what you can tell me. The next one should be x to the fifth plus, now you don't know anything about the number yet, right? So let's just wave our hands at that. But the variable would be x to the fourth and then h and then plus. You don't know anything about the number, but it would be x third, h squared. And then you don't know anything about a number, but it would be like x squared h cubed, and then plus. You don't know anything about the number, but it would be x first power h to the fourth, and then again, you don't know anything, h to the fifth. Yeah, that'd be correct. The only thing left for you to do would be to determine the numbers.
You said this was called binomial?
This is binomial expansions, because this is a binomial, right? And remember how you were saying factoring? I said, no, it's called expanding. These are the expansions of a binomial expression. Understand this? Now let's try and fill in these numbers. Well, look at down this side. What does the first one always have on it? What's the number in front of the first one?
1.
It's always a 1, right? And notice the ones on the ends. What's the number on the ones on the ends?
1.
It's a 1 also, okay? Now what I'm going to do is I'm going to go in here and I'm going to highlight all the numbers so you can see them. 1, 1, 1, the coefficients. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. All right? And then I'm going to draw something to connect this all together. The blue here is what's called Pascal's triangle. So take all the letters out, okay? Just look at the blue. It's called Pascal's triangle. If I drew it on the side, which won't come on camera, it'd be 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, right? That's what we're looking at? Okay, so look at how this works. The edges are always 1s, okay? So the first row has one number. The only thing it could be is 1. The next row has 2 numbers. And the rule is that the edges have to be 1, so it has to be 1 and 1, doesn't it? The next row has 3 numbers. The edges have to be 1, right? So that takes care of these 2. So the only thing was, how did we get this, right? That number right here, this 2, comes from adding the 2 above it. These 2 right here, added together gives you 2.
And then you add the other. And you
So how did we get 3?
get those
1 and 2. How did we get this 3? 2 and 1. See that? Here it would be like this. This 3 comes from here. This 3 comes from here. Got it? So do you see where I got the 4 from? 4 was this 1 and this 3. Do you see where I got the 6 from? 3 and 3. This 4. 3 and 1. So anyone want to tell me what the numbers are going to be here? 5. 10. 10. 5. That's it. That's the expansion.
That is awesome.
Yeah. Save you some time. Sure.
Yeah, same.
Wait, why didn't they teach that?
Yeah, seriously.
I don't know. Did you ever have to expand something further than like to the third power?
Not really, like square
Yeah?
or cube.
I don't know. It would have been nice to know.
Yeah.
Yeah.
So it would have been nice to know.
Do they teach this further on, like in pre-calculus?
No.
I'm just gonna have to remember.
I've never seen this in any of our books.
Why is this not taught more?
Is anybody else?
I don't know. I mean, I guess it
You
is.
gotta take a test.
It's gonna be on YouTube, right?
Well, yeah.
I did see.
It's on the video also, but some people don't like to go back and watch the video.
We can't see the triangle that has it all.
Yeah. Yeah, so normally if someone's referencing, if someone says, hey, you know, Pascal's triangle, they're not talking about Pascal's triangle has nothing to do with binomial expansions. Pascal's triangle stands on its own. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1. I could keep going forever, right?
Seems like a decent way to pass the time.
Yeah.
Just solve as far as you want.
Until you
to.
die?
Yeah.
Okay. We could do that. But each one of these has this right here, right? This one right here are the coefficients to the expansion of x plus h to what power? 6. So the first number you see here after the 1 is the expansion number. So it's the thing that's hard with this is, you know, what would x plus h to the 12th be? What you would have to do is actually draw out the first, you know, you'd have to draw out enough of these to get your triangle to figure out where it is, right? There is actually a shorter way where you can come up with the coefficients much faster, but it uses factorials, and if you've ever seen factorials? No? So there's a formula, like, have you ever heard of this, like n choose r? Have you ever heard that before? Something like you have a box full of, or you have a room full of 20 students. How many different ways can I choose a group of 5? So like I could go and say this 5, right? That's one way. And then I could say all of you except not you and you instead. So that's a different 5. How many different ways can that happen? This is like a statistics thing. You get into what are called permutations and combinations. You can use this to actually get these numbers without using Pascal's triangle. But we're getting way off topic, sorry.
Yeah, you got me now.
Well,
Maybe like after class.
not today, but I mean, I can hang out for a few minutes, but I can't hang out for an hour. All right, so the algebra starts to get more and more complicated, all right? So let's do D. I think I'm going to skip C. Let's do D. So we have a new function. Well, you know what? I want to adapt it even more. I make it a little harder. How about we do 1 divided by the square root of x minus 3? All right, this would be a problem I would definitely give on a calculus, in a Calculus 1 class as an exam problem. Now, they have to do a little more than what we're doing, but their first step is the difference quotient. All right, so and that's the part they mess up. So let's see if we can do difference quotient on this. All right? So find the difference quotient. We need f of x plus h minus f of x all over h. So what's the top left going to be? 1 over square root. Then what? X plus h minus 3. You don't necessarily need it. You could put it, but it doesn't matter because I'm not distributing anything to it, so that would be it. That's f of x plus h. That's x plus h plugged in right there.
Oh, okay.
See, so it's inside. It's with the x. It's not outside the root or anywhere else. It's in there. Do you see it?
Yeah, okay.
Okay. Now, I want to subtract from that what? F of x.
1 over the root of x cubed.
X square root of x minus 3.
Oh,
Right? All of this over h. So in order to get the h to cancel like we want, in the last problem, the h had to be on top, right? For that to happen, we needed to pop an h out of the top somehow. And what worked for us last time was putting these two together, right? Getting a common denominator. Same story. We're going to get a common denominator. What's the LCD? So what are we going to multiply top and bottom by here?
the root of x plus h minus
Yeah, the whole thing. It's ugly, but that's what we have to do. There's no way around this. We multiply this one right here, top and bottom, just this one, by this. And then on this one, we multiply top and bottom by what? So square root of x minus 3, square root of x minus 3. Y'all with me? Put them together. So what does your new numerator turn out to be? Let's see.
the root of x minus 3
Okay, root of x minus 3.
minus the root of x plus h minus
All over your new common denominator. Careful.
Oh.
Right? What's the common? It's these two together multiplied. I'm just going to leave them apart. I'm not even going to try and multiply them through. Then all of this over h. And let's make sure everyone's on the same page with that before we move on. Does anyone have a question over any of that? You comfortable with that? What do you got?
It seems like when you're finding the difference quotient, you're plugging it in. It's actually a combination of the difference quotient plus whatever variables that they give you. That's what it seems.
I'm not sure I follow that.
Because it's kind of like you're plugging in x, like, so let's say, let's see, because like for this example is like x minus 3, so then you're putting the x plus h where that is.
Right here.
Right,
Yep. And that became this.
right.
Uh-huh.
And then you're taking the other, well then there was no other, but, and then I guess you have to minus it because of that formula.
Yes.
And then that, the x meaning x minus 3 over 1.
Yeah, this right here is just the original function, right? So this top right corner will always be just the original function.
Right, I guess if we wanted to, we could put that.
You could, but because it's one term, I don't need it.
Okay. I just want to make sure that I'm.
Yeah, no, that's why I'm making sure we're all on the same page. All right, so do we see an h canceling here? No. Last time we had an x plus h cubed there, didn't we? And we just expanded it, and then the x cubes cancel, and we were all happy about it. Maybe we weren't that happy, but it worked. So we cannot distribute this negative through and get rid of the root, right? I mean, there's no way we can do that. I heard you want to
I was gonna say square root it, but
square it,
yeah.
like just square it to get rid of the root.
Yeah.
Okay, is that something you can do? We need to have these conversations. We need to have these conversations. This is, okay, let me ask you this. Just forget that for a second. If I ask you to solve this equation, it's a radical equation.
Yeah.
You would square both sides.
Yeah.
You're allowed to square both sides, right? You could have extraneous solutions because you squared both sides. You have to check your answers. But yes, I agree with you. You are allowed to square both sides, because squaring both sides does not it changes it, but it doesn't ruin the solutions if there are any. It doesn't change the actual problem. If that makes sense. Now, let me just give you this. I'm going to tell you right now. I'm going to give you an expression as opposed to an equation. can I just square that?
Yes.
Is it the same thing anymore?
No.
It's not, and there's a problem. See, when you square both sides of an equation, it's kind of like what you're doing here also, so you maintain equality. When you have a 4 and you square it, it's no longer 4, it's 16. If I just come in here and start squaring, I'm not even working with the same thing anymore. It's not the same expression. So you are never allowed to just square an expression unless you plan on square rooting it again, because you got to undo the squaring. So this is an expression, it's not an equation, it's not set equal to 4 or something, so we cannot just square it arbitrarily. Understand the difference? This is a big thing. I see it happen again in calculus. People are like, well, anytime I see square roots, I want to square them. Only when you have equations you can do that. So what can we do? Reciprocal of h. You can mess with this. Remember though, we want something up here, right? We want h up here. Okay, so I'm going to come in now with something. This is just one of those things. This is why you take classes, right? To learn these little kind of tips. Okay? I have this up here, right? I don't like square roots. You want to square it, you can't, but I have a way we can do it. We can still get rid of these roots. I'm going to come in here and I'm going to multiply by another 1. Okay, same thing on top and bottom. Guess what I'm going to use? The conjugate. That's right. I'm going to use its conjugate. Now, we did talk about conjugates, didn't we? The conjugate is the same expression, but you change the sign between the two.
Why is that now?
Because this is a 1,
I see.
right?
I'm sorry.
So I'm looking at this up here. I want to try and get these roots to go away, right? So what I do is I rewrite this with a plus between, I put it right here. That's a 1. So I have not changed the problem, right? Right, multiplying anything by 1, it's the same thing? Okay, so that is a fair move. That's a fair algebraic move? Okay, now the effect that this has is what I want, because when you actually expand these two, multiply these two together, right? Here to here, here to here, here to here, here to here. What can you tell me about the middle multiplications?
They're going to disappear.
They're gone, right? The only thing that happens is the outside ones, which is why we did it, right? Do you remember us talking about conjugates? Did we?
Yes.
I remember talking, it feels like I did. All right, so here to here, that first one matters. What's this root times this root?
That's going to just be itself.
Itself, right? No more root? Okay, so I'm getting on the top x minus 3. And then when I do the last multiplications, which is going to be this one times this one,
It's going to be it by itself.
it's by itself again, right? It's everything that was under the root, but
It's negative.
it's negative because this and this. So I have to be really careful here. It's minus everything that was under the root. Right? Negative and positive is negative, so I'm going to subtract whatever this root and this root multiply to be, which is everything under the root. Yeah? So I have to subtract everything that was under the root.
So we can just go ahead and distribute it now? Or
Oh, you could have done it, yeah, but I just want to make sure everyone knows where it came from. Now look at this disaster of a denominator now. Okay? I have this, right, times this, and I'm not going to touch it. I'm just going to leave it like that. Because what's my goal? Get the h to cancel. I really don't care how complicated this looks. So it's these two, which were being multiplied, weren't they? Right there? Times, but this is two terms, isn't it?
Yes.
So I need a set of parentheses here. Root x minus 3 plus root x plus h minus 3. Close it off. All of that divided by h. I said algebra on steroids, didn't I? That's what calculus is. And what I'm trying to do in this class is prepare you for that. Yeah, algebra on steroids, that's calculus. Calculus on steroids is called more calculus, calculus 2.
What you said is basically on covering everything that we're
Hmm?
basically you said everything that we learned.
Yeah. All right, now you're free to go ahead and distribute the negative, and good things are going to happen. Do you see that? Good things are going to happen. Any questions on any of this expression here, other than it being ugly? It is, right? Get used to it.
Would you say for this kind of problems, you use the conjugate, that's like the most efficient way?
Yes. So there were a couple of things that we did, right? The first thing we did was we got a common denominator, put them together. Once we did that, we realized the numerator had radicals in it. When we see radicals, we don't like them. We like conjugates to come in and wipe them out. So that's what we've done. So this is just one of those tools you have in your toolbox now. Just you can pull the conjugate out whenever you need it, right? That's the new numerator over what, this again, and then all over h. I wrote all that again just to distribute that negative through, right? Just to distribute the negative through, but we get good cancellation now. X's are gone, right? 3's are gone. And now you have an h, a negative h on top, right?
So it'd be all over -1.
So you can cancel those h's now at this point. And when you cancel them, don't forget you'll be left with a -1 on top, right? This will be a -1 when it's canceled out.
All over that.
All over that junk. And that's your answer. So your final answer is, I'm going to cheat here. I'm going to use this work.
Work is smart, not hard.
Yeah. There you go. That's your final answer, right? Oh, -1 over that.
Is that it? You got that one wrong.
Yeah, I know. There it is. A lot of work, huh? All right, so any questions?
That was a long problem.
Yeah.
And that's just the first step in it?
Well, the calculus part of this now is just to now let h go to 0. And let's just look at it, because everyone's going to have to do this later at, if you take Cal 1, which is most of you, right? All of you?
Yes.
I think all of you. Anyone not taking Cal 1? Okay. So in Cal 1, what you'll do is you'll say, now let h go to 0. What would happen if h goes to 0? The numerator would stay the same. This would become root x minus 3. Look at this right here. If that h goes to 0, don't I get another root at x minus 3? Then times in parentheses root x minus 3 plus, and then right here, if that h goes to 0, I get another root x minus 3. Okay, so if I do these two together, doesn't the root go away? It's just x minus 3. So -1 over, in parentheses, x minus 3. And then if I put these two together, an apple plus an apple is 2 apples. So this is times 2 of these root x minus 3s. You with me still? And no? Yeah. Okay. And then now, at this point, I recognize something. I recognize that this is the same as, I'll put the 2 out front, this 2 out front. This is the same as x minus 3 to the first power times x minus 3 to the half power, right? Because isn't a square root a half power? And if I have the same base and different exponents and they're being multiplied, I add exponents, don't I? So yeah, that's it right there.
Okay, so how did you get the half power?
That's what a square root means. Square root of x is the same as x to the 1/2.
And then how did you pull the 2 out?
The 2 is right here is being multiplied. See, I put these two together. Something plus something is 2 of them, right?
Yeah.
So I had 2 of these roots. There they are. 2 of those roots. And then now I pulled the 2 out in front. And then I just rewrote these as powers and then put them together. That's it. And this is actually in Calculus 1, this is what's known as the derivative of the function f, right? So someone gave us a function f. We did the difference quotient. We let h go to 0. We simplified the answer. This is called the derivative. Have you all ever heard that calculus is, they call it differential calculus? No?
Oh,
Differential stands for derivative.
Integral?
Integral calculus is Cal 2.
Oh, really?
Yep.
Okay.
So differential calculus is Cal 1.
Okay.
And this is what you're doing is you're taking derivatives of functions. And then in Cal 2, you actually have to go backwards. So you have to go from this back to where it came from. It's much harder. But don't be too worried. This whole thing with letting h go to 0, this is hard. This is the hard part. Then in Cal 1, what we do is we give you shortcuts. We give you these little rules that you can use that make it much faster. Much faster. All right. And I'm never going to get through this class. We're gonna end. It's good though. I think everything we're doing is positive. We're in the right direction. Okay. So. All right. So we're going to say we're done with 3.1, and we're going to move on to 3.2. Oh yeah, this is my class, my Cal 2 class today. So you see these 3 problems right here?
Yeah.
Right there? Those 3 problems took us the entire class. So my entire 1 hour, 40-minute lecture today was me doing those 3 problems. And that little symbol you see in the front like that, that's basically that's telling you instead of take the derivative, that's saying do it backwards for each of those functions.
I'm glad somebody was on that.
You'll understand it. It's like a language, right? You just have to.
Cal 2, he says
It literally is just a new language right there.
It's all it is. It's a language. Cal 2's what?
says the hardest of the 3.
That's what most people say, yes.
What's your opinion?
I think I agree. But I only agree because of this. By the time you get to Cal 3, you've survived Cal 2, so you're a mature math student. So the challenges in Cal 3 don't appear to you to be as much because you understand what that level is. So you're kind of used to it. In Cal 2, I don't think you're used to it, so you get punched in the face real hard right in the beginning, and then you either survive or you don't. In Cal 3, you're like ready for the punch, and it never really comes as hard, if that makes sense. That's a good analogy. I like that. I'm not good with analogies. That wasn't bad.
It's like first one's like a wake up and then they punch you in the face and then you're like, whoa, and then you're like.
Yeah, you're always ready for that. Okay, let's get into 3.2, graph of a function. Most of us are familiar with the basic concept of the graph of a function. So I'm not going to spend way too much time on this. X, y is some function of x, right? And then we graph it. So all of the points on the graph represent the solutions to the equation. This is a 2-dimensional space. Okay, 2-dimensional space, which you may or may not have ever seen. We've seen that, right? What did I tell you that stood for? That was all real numbers. That was a number line, right? Right? Everything on the number line. Now, if you have 2-dimensional space like this, we do R2, R squared. And what it is basically is 2 number lines drawn perpendicular to one another. Then R3 would be what? 3-dimensional space. And then R4, well, now you're going to get out of something we can see, right? Yeah, we can go higher dimensions, but we're going to focus our attention on R2 in this class, right? R2 is called the Euclidean plane. Euclidean plane. Euclid, mathematician, and we have a lot of rules in Euclidean geometry. Tell me some of the rules in Euclidean geometry. I'll give you a hint. Like Euclidean geometry. So this is called the Euclidean plane. Euclidean geometry. Did I spell that right? That doesn't seem right. Yeah, I'm not a spelling major. That's what I'm doing. I'm studying up here doing math. Okay, Euclidean geometry. Some of the things that we have, like if I have 2 lines and they're parallel, what can you tell me about 2 parallel lines? They'll never intersect, right? That's a property of Euclidean geometry. That is a property of Euclidean geometry. Does that mean that it's always that case? Do parallel lines ever meet? Not in Euclidean geometry. They don't. But they do in other places. I'll give you an example. Anyone in here an art major? Or not an art major, but have taken art classes, like to draw? Anyone